right, so good evening, everyone. Again, we'll start up again here with quantum mechanics. So this begins our third chapter. Again, the focus of the atoms first approach is to talk about all the different parts of the atom so that we understand its different dynamics before we get into any actual chemistry. So quantum mechanics deals with electron properties. Okay. So the first part of this, so we have a couple different things here. So the wave properties, so there is a calculation that deals with the wave-like properties of electrons. All right, and so we should be able to do calculations with this one equation. It's a very simple equation, but it deals with the speed of light and the frequency and the wavelength of an electron. Okay, and so we should be able to do very basic calculations to find either frequency or wavelength of an electron. Okay, we're going to talk about the electromagnetic spectrum, which I'll probably skip to first and just talk about the electromagnetic spectrum. All right, because that's, we'll start this video off and just talking about we'll do the interesting part first, and we'll talk about the electromagnetic spectrum. In this case, there is not so much in the way of calculations, but we should be able to organize the electromagnetic spectrum based on frequency or energy and understand what it is composed of. Okay. Then we'll talk about different quantum mechanic models. Okay, so quantum mechanics deals with probabilities of where do we find electrons. And so there are, at the general chemistry level, a variety of ways in which we can try to boil down the insane calculus of quantum mechanical models into very easy explanations. Okay. And then lastly, we have the periodic properties, which we've already talked about some of these, and a lot of this is really identifying various trends of the periodic properties, knowing which element is higher in electronegativity than another. Okay. And so this one has less in the way of math. Okay, so up until now, the first couple of chapters are heavy in calculations. This chapter is more in memorization, and do you understand the conceptual frameworks of what we're going to talk about. All right, so I'm going to skip right to the electromagnetic spectrum here. So I'm going to skip through a couple of slides here, all right, that we will come back to tomorrow or next week. So the electromagnetic spectrum deals with a whole range of energy. Okay, we have light in different frequencies and wavelengths that make up the electromagnetic spectrum. Our general human interaction with the electromagnetic spectrum deals with visible light. Okay, our eyes interpret a portion of the electromagnetic spectrum in the light that we see and the colors that we perceive. Okay, now we have generally some experience with other parts of the electromagnetic spectrum, but generally we may not have put all of these things together as being related to one another. Okay, so in a test kind of arena, okay, you would basically need to know the parts of the electromagnetic spectrum, which are as this: radio waves, microwave, infrared, visible light, ultraviolet, X-ray, and gamma. Okay, so this covers a range of frequencies of light from 10 to the 4th hertz, which we'll talk about in a minute, is what, or we would have talked about what a hertz was, but it's essentially a frequency value, how often something passes in per unit of time. Okay, from 10 to the 4th hertz up to 10 to the 24th hertz. So that is obviously an increasing value. Okay, we have a low energy part of the spectrum, radio waves, and high energy in gamma ray. Okay, our visible light that we perceive things in is that small little sliver in the middle. Okay, there is a massive amount of information in the electromagnetic spectrum that we do not perceive. Okay, our eyes do not pick up the bulk, the majority electromagnetic spectrum. Okay, but these various things are usable. Okay, we use them in other ways throughout our first world nation society in general. Okay, so radio waves are generally very low in frequency, lower in energy, but have very big waves. Okay, you'll notice that the difference of the wavelength and the frequency, they are inversely related. Okay, so a smaller or a small frequency is a big wavelength. Okay, the waves are very big, in like kilometers size big. Okay, so we generally use these things for information transmission. Okay, we use this in astronomy. Okay, so a lot of these are astronomy references. So we'd use microwave, or radio wave antennas. And so as we send out a radio wave, it is like doing an X-ray, right? So except it's a very low energy, right? Very big wave. The wave particle comes, we send it out, it bounces off stuff, and we collect the information within a big dish. Okay, so the dish has to be big, right, in order to collect all of the receiving information, to gather that information. Okay, think of it like the pupils in your eye, right? So when it's dark out, your pupils get bigger, right, in order to accept in more light so that you can see. Okay, your eyes, your pupils dilate, they get small to limit the amount of light when there's too much information. Okay, so in a radio dish, we need a big radio dish in order to accept a lot of information. And so we can actually see things like the image on the right. We can see the actual motion of objects because of the way that the radio waves come back in the timing in which the data comes back. We can actually visibly map to actual rotation of objects, so we can see things moving. Okay. There's a variety of ways that these are used. At least radio waves are used for a variety of different kinds of imaging. Oftentimes you'll hear people talk about things like redshift, right? And so we can see, so this is the rotation of a galaxy. So we can see and know the part of the galaxy that we see from a telescope, that we can map to a telescope that is moving. We can tell the rotation of objects, that the blue part is moving towards us and the red part is moving away from us because the frequency of those values are different. Okay. As we move up slightly in energy, we have microwaves. Okay. Most of us are familiar with the use of microwaves just in the fact of heating our hot pocket, right? But it's for more than that. Okay, we can do data transmission via microwave. Okay, Doppler radar is a microwave image, or is a microwave radar for weather. You'll notice weather is a common theme here in how we can use parts of the electromagnetic spectrum. Okay, we get decent penetration through clouds and dust and smoke and things like that with different parts of the electromagnetic spectrum. Okay, our visible light, we can't penetrate clouds with our visible light, but other parts of the spectrum see right through those objects. Okay, here we can look at, I believe this is, let me move my image up. Right? So we have a microwave satellite images. Right? We can watch the sea ice formation. We can look at different parts of the Earth. This is Mount Fuji. There's a picture of Mount Fuji in microwave. Okay? And we don't see in the microwave spectrum, but we can interpret microwave data to an image. Okay. Probably one of the most important aspects of the microwave part of the spectrum is the cosmic background radiation left over from the Big Bang. Okay, this is a picture of the beginning of our universe. We can see the remnants of the Big Bang in the microwave region of the electromagnetic spectrum. So this is probably the most, at least science-wise, the most important aspect of how we use the microwave, or at least for me, I would think was the most interesting version of the microwave spectrum used. Okay, moving up a little bit, we have infrared. Okay, now this is going to be a section that most people are familiar with. Okay, most people have seen infrared in some portion. It's a very popular way to popular vision used in movies and things. Right. In the infrared, we have long wave and we have shortwave IR. We have different parts of it. Okay, shortwave IR is the energy that we get from the sun, versus long wave IR is radiated from objects. Okay, so our bodies are warm. Our bodies radiate heat in long wave IR. Okay, so we can see things like our bodies in long wave IR because of the heat. So this is currently how this is kind of one of those things that you'll see here is that it was probably in the news not too long ago. Again, it was something that it came up during the first SARS epidemic. Was when people were traveling on the airplanes, and then they were spreading SARS from airplane traffic, and so then they were trying to use infrared as a way to take your temperature virtually, right, or remotely, right, before you got out into a plane. And so this is another thing that it has come back up recently, now that we need to probably try to screen people, trying to screen people at a distance, just tell whether or not you're running a fever, right, before you go through checkpoints. It doesn't work as well as obviously as like a regular temperature thermometer, right? So it has too many variables in our body's dynamics to get a good actual core body temperature reading. But nonetheless, it is a feature of infrared that our radiated body heat, we can measure it in some aspects. It's just a matter of how accurate that is, especially when we're only looking at, humans run 98 degrees Fahrenheit, right? If we're talking about our crappy scale, to 102, right? Ish. If you're more than that, you're probably not walking around like at the grocery store or going on a plane, right? So you're only talking about 4 degrees difference in body heat to whether or not someone may or may not be sick. These things don't tend to shade well enough to be able to give that kind of, again, this goes back to our discussion of like significant figures. Okay. You're trying to read 4 milliliters out of a gallon jug. Yeah. The sig figs on a gallon jug are not going to tell you the difference if you added 4 milliliters or not. Right? So Same kind of thing works for IR too, right? So here we can look at our subject here of looking at it through the different spectrums, different parts of the spectrum in infrared. Okay, so the shortwave IR, okay, is not the radiated heat, and then as you get into mid and long range IR, you begin to see the radiated body heat image. Okay. We can use infrared imaging or infrared satellites because if we wanted to look at things like forest fire, right? So you can't tell where really the fire is going through the smoke. Okay, if you're looking at it from a visible satellite image. As opposed to an infrared, we can tell distinctly where the fire patterns are if we wanted to put someone in to deal with it. So there's a variety of commercial technologies that are out now that look at how do we deal with, again, the short and long range IR or short and long wave IR. You get different kinds of imagery. So obviously it doesn't have to be blurry. We don't have to use the long range. We can use a short range IR and we can get a very crisp image in total pitch black, right? And so you can actually see that the black stands out very well in the dark, right? And so we can use, we use infrared imaging for satellite and for astronomy images because we can tell heat patterns of various stars. So we can actually tell the infrared radiation of a star can tell us about its age, okay, how hot it is, right? So a hot star versus a cold star, we can see in the infrared. Okay. Most people are commonly see these kinds of things. If you're not in the military business, you at least see it from video games probably. This kind of infrared imagery. So in this kind of environment, the human body heat is radiated very well against the cooler atmospheric background. So you might be wearing black at night, which actually stands out very nicely in the infrared. So an infrared camera wearing black is only going to make you better. Only makes you stand out even better, almost. So there's no tactical advantage gained from a camouflage in the infrared. We already looked at that. We can see body heat. There's medical applications of the infrared. Okay, we can look at things like obviously the blood flow in the body. Okay, you can see where the veins or there may be potential blood flow issues where you're not getting sufficient circulation. And we can see that in the infrared that may not be apparently visible. Probably commercially, people see infrared things and like infrared cameras from commercial aspects. If you get an energy inspection on your house or just a general inspection on your house, a lot of times the inspector will use infrared, particularly for things like looking at your attic space, right? So they can check your insulation, right? So when I bought my house, they can just shine the camera up at the ceiling and they can check to see where the insulation was bad. So they'd say, oh, over here you got a cold spot over here. So maybe the insulation's kicked over and not spread out as nice, right? So they can tell where the cold and warm spots are. If you look at your windows, if you're getting high efficiency windows put in. They can take a before and after picture of your window heat loss, right? So if you're getting double pane windows with the nice xenon or argon, so some kind of noble gas pumped in between, again, noble gases are inert. They're good insulators. And so that's why they use them in windows. And so if you're paying more for an expensive window, you probably have a decent like xenon or krypton gas in your windows that has a good insulating factor. And so you can see the difference in the heat loss of your house before and after replacing windows. Obviously, again, we use infrared for things like weather patterns. We can see the thermal variations in a storm in the infrared. What's cool is like we can look at the entire Earth. We can look at the temperature variations across the globe at any given time in the infrared. You can watch, basically you can watch global climate changes in real time. We also use infrared for organic chemistry. Okay. Molecules, carbon molecules vibrate in the infrared. And so when we look at an infrared of this molecule, this spike right here at 2300 is telling us this kind of vibration is occurring. Versus this same part of the molecule has a separate kind of vibration. This vibration pattern from the waggle is here about 600 wave numbers. So organic molecules, we can tell the structure of organic molecules from the infrared. And so this is something that generally when you get to organic chemistry, you would spend some time learning about how can we tell the structure of molecules from infrared. And we sometimes will have an infrared spectrometer in the lab, and we can look at how molecules look. Right? And so it is not a mystery. When we synthesize molecules in the lab, we can tell what they look like. We can do a variety of things like infrared imagery to tell what its structure is. These structural patterns are given off in different vibrations of a molecule. Okay, this back and forth wiggle is a different wavelength than the up and down waggle of the same molecule. So we can tell what its structure is. Okay. Our eyes, so visible light is important to us because this is part of how we see things. It's a relatively small wavelength. Our eyes are even not particularly the best of within the animal kingdom. Okay. People often use the human eye as an amazing evolutionary feature, when it's not even really that amazing because there are other animals that see in a slightly wider range of the spectrum than we do, that have a better dynamic range to things like birds. Okay. And like variety of other animals like the octopus and things like that have they can see slightly further into one range of the infrared or the ultraviolet. as we move up into the ultraviolet, okay, ultraviolet is slightly higher. So ultraviolet is on the kind of our purple end of our spectrum. So this is generally why we see things like the black light in purple. Right. One of my favorite quotes from Richard Feynman. Again, I put the video on there of Richard Feynman doing the scientific method lecture. I also posted his lecture series that's available. And amazing lectures to listen to. But if we could see the world from how birds see them or how bees see things, the dynamics would be in, we would get an entirely different view of the world. Bees actually co-evolve with flowers. Flowers co-evolve with their pollinator. Right? Insects that pollinate flowers, those flowers are more readily visible in the ultraviolet to attract their pollinators. Right? So bluer flowers that are brighter in the ultraviolet attract insect pollinators. Right? So your red flowers are probably looking for some other kind of pollinator, probably things like, a bird or something, or some other kind of moth, right? But flowers co-evolve to match their pollinator, to be more attractive to the insect that they use to transmit their pollen. We see the ultraviolet as kind of a purple range because that's kind of how our eyes interpret that part of the spectrum. If you've watched Animal Planet, they go out with the black light and see the scorpions in the desert because their exoskeleton radiates in the ultraviolet. Obviously, we can use, people have talked about using things like ultraviolet as a way for decontamination. We want to decontaminate ourselves or our groceries or something. Now we use ultraviolet for decontamination, but the technology for that is a little bit outside the range of normal everyday ultraviolet, right? It's not like going to the tanning bed, right? Killing bacteria with ultraviolet requires a specific amount of energy, a specific wavelength, a specific contact time. So those kinds of things are a little more controlled than just wax on, wax off, magic happened and my bacteria are gone. Doesn't quite work like that. Okay. Here's kind of a culmination of some of these spectrums of light for astronomy. By looking at things in space in different parts of the wavelength, we get different kinds of information. We gather different pieces of data to better understand the universe around us. How we understand the universe, how we understand different parts of our own galaxy are a function sometimes of our technology, our ability to see further or in a different spectrum yields different amounts of information, that it gives us different data that builds on the things that how we see things, how we understand the universe around us. Ultraviolet obviously has some other, more, whether they're kind of artistic areas. So we have art and things like that. You got, photography in the ultraviolet. There's ultraviolet lenses for things. Going up, X-ray is a pretty standard one. We see this in dental and standard X-rays. Okay. Our bones are higher density, so they absorb the high energy X-rays. Nowadays, our technology is mostly aided by computers, so we probably don't. Oh, well, I wouldn't say don't, but I don't know how many people nowadays use the X-ray plates like I used to use back in the day, where you get the plate that you jam underneath. Well, I used to work at a vet clinic, so you get the old plates that you jam underneath there, and then you zap them, and then you take it out, you put it in the machine. It's like developing a photograph. Right? Now we have computer technology that allows us to take those same slices and build a 3D model. One of the more interesting aspects of X-ray technology that is not your standard, I'm taking pictures of my skull, because I have access to an X-ray machine on a weekend thing. On the left image is the X-ray diffraction pattern of DNA. Rosalind Franklin took this image. This image is what allowed Watson and Crick to develop the model for DNA. What does our DNA look like? Without this image, they would never have cracked the code on what DNA looks like. On the right, you have an X-ray image of a viral particle. Our ability to image smaller is getting better. Pretty soon, you can kind of see the protein coat of a virus. The better we can understand its protein structures and dynamics of its surface, the better and faster we can develop vaccines and therapeutics against them. Okay. The rest of these are common X-ray things, obviously your baggage, and we use bigger X-ray scanners at the border. And then lastly, we have gamma rays, which we don't really deal with here on Earth. They are more extraterrestrial origin type things from like neutron stars and black holes are generally where we see the cosmic value of gamma rays rather than our terrestrial energies. We can use some versions of cosmic rays, and we can try to harness some of these cosmic background radiation things for various things. Like obviously, I think one of its niche areas is things like imaging, that we can capture. That obviously the cosmic rays pass right through all kinds of matter, so we can use it for things like imaging of rock and stone for like pyramids, so we can see the voids within a structure. All right, and so that kind of concludes our electromagnetic spectrum. So really the things that you need to know from this are, if I gave you a variety of pieces of the electromagnetic spectrum, you should be able to put them in order, high to low, low to high, based on the different feature. We're talking about high and low energy, high and low wavelength, high and low frequency. You should be able to put them in order. So there's no math here. It's did you memorize the electromagnetic spectrum? Do you know what order these things go in? If we were to put these in order of high to low energy, which one is the lowest? Which one is the highest? What order do they go in? Okay, so this is the kind of problem that you would have to do for the electromagnetic spectrum. Okay, all right, well, that concludes our portion, or at least our introduction for the electromagnetic spectrum. And so we will come back to this next week.